So, we have read the recursion and the recursively defined sets, functions, sequences, and we have also learned that how to design the recursive algorithms. Today, we will read the recurrence relation, which is very much related to this recursion, and we will see that how given a sequence that each term is related to others and how we can get a explicit formula, how we can get a recurrence relation with that thing, and how to solve or what do we mean by solution. So, we will do the framing recurrence relation and solving recurrence relations. So, we will read the recurrence relations. So, first we define a recurrence relation. You can write that a recurrence relation for the sequence, we have earlier read the sequence or recursively defined sequences. So, for the one sequence A0, A1 to An having n number of sequence. So, it is an equation that relates n to certain of its predecessors. And the predecessors are A0, A1 up to An minus 1. So, recurrence relation gives a relation that how An is related to its predecessors. Now, we have already read many sequences where this relation exists. So, one popular example is that Fibonacci sequence. How we have defined that Fibonacci. So, for Fibonacci sequence, we know that nth Fibonacci number Fn, the nth Fibonacci number is An or Fn Fn is Fn minus 1 plus Fn minus 2, and some initial conditions are given that F0 equal to 0 and F1 equal to 1. So, this is an example of a recurrence relation, because Fn is related to its predecessors Fn minus 1 and Fn minus 2 with some addition, and these are my initial conditions. So, this is an example of recurrence relation. we take an example of compound interest, how to compute the compound interest. We take one example. Say a person invests rupees 10,000 at the rate of say 15% interest, which is compounded annually. Now, we want to find out the total amount at the end of nth year. So, we can write the amount that at the end of nth year we can get that n is n minus 1, that amount that at the end of n minus 1th year plus the interest, that means it is 15%. So, 0.15 or 0.15 into n minus 1. So, I can write this is 1.15 into n minus 1. So, here n relates to only one predecessor n minus 1 in this way, 1.15 into n minus 1. So, this is a recurrence relation. This is a recurrence relation. Now, if I take that n equal to 3, say n equal to 3. So, A3 is 1.15 into A2. I can write 1.15 into, or again A2 is 1.15 A1. So, this is square A1 is 1.15 cube into A0. Now, what is my A0? Because at the beginning it in 10,000 was invested. So, it is 10,000. So, I can write that it is 1.15 cube into 10,000. So, I can generalize this thing as that n equal to 1.15 whole to the power n into 10,000, and we call this is a explicit formula. This is an explicit formula or of n. So, this is my recurrence relation, where the nth term, how it is, it gives a relation, how it is related to the predecessors, and it gives directly, that means it is a function of n, the explicit formula. Now, we have read the recursive algorithm also. So, the same, for the same example I can write the recursive algorithm. that I can write the function that if it is compound interest n, that means at the end of nth year. Now, if n equal to 0, that means it is my initial condition or the terminating step, then return 10,000, else it will return that compound interest, right, 1.15 into compound interest n minus 1. So, with this simple example we see that we get the recurrence relation, explicit formula, and this recurrence relation, that means the recursive step, that if we give a code of that, then it gives you as the recursive algorithm of that thing. Now, we take another simple example, but it is very important when we will see the we will try to solve the recurrence relation. So, earlier we have read one example of set, that say let Sn be the number of subsets of an n element set. Then how can I give a recurrence relation for Sn? If we remember that, say Sn be the number of subset, then Sn minus 1 is the number of subsets of an n minus 1 element set. So, let initially I have we start with the set having n minus 1 element. Now, if I add one element to that set, so that it becomes an n element set, then what will be the number of subsets? So, the number of subsets or of a set having n elements, I can write this equal to the number of subsets having n minus 1 elements, subsets of a set having n minus 1 element plus if I add one more element to all the subsets of these n minus 1 elements. That means, this is if I let the nth element be, let the nth element be A or n. So, number of subsets of a set having n minus 1 element, which is without A, and here I can write the number of subsets of a set having n minus 1 element with A. This is with A. Now, clearly this is my Sn minus 1 and this is also Sn minus 1, only difference is here in these subsets A was not there and in these subsets S is there. So, this becomes 2 Sn minus 1. So, Sn equal to 2 Sn minus 1, this is my recurrence relation. This is my recurrence relation. Now, we can get the explicit formula also. For this example, if I start with that Sn equal to 2 Sn minus 1 is 2 into 2 Sn minus 2 is 2 into 2 into 2 into Sn minus 3. In that way, if I continue, I will be getting that 2 to the power n, which is here 2 cube into Sn minus 3. This is actually 2 cube into Sn minus 3. So, I can get 2 to the power n S n minus n is 2 to the power n S0 and our S0 is 1, which is the empty set. So, this is 2 to the power n. So, Sn is 2 to the power n and this is my explicit formula. For the number of subsets, Sn is the number of subsets of a set having n elements. So, we see that how we can frame the recurrence relation and we get a explicit formula. Actually, this explicit formula is called the solution, and a solution that which satisfies the sequences we get. Now, we get another example we see. So, we find the number of n bit strings, find the number of n bit strings that do not contain one one one. Say a particular bit pattern is not there. then how to solve or how to get this number? So, let the solution is, let Sn be the number of n bit strings that do not contain 111 pattern. Now, we want to find out the recurrence relations. Actually, here that example will be that find the recurrence relation. Because first we try to frame the recurrence relation, how to frame the recurrence relation. So, our problem is find the recurrence relation, where for the number of n bit strings, let me rewrite, for the number of n bit strings that do not contain 11. Now, let Sn be the number of n bit strings, then obviously Sn minus 1 be the n minus 1 bit string that do not contain 111, and then similar thing for Sn minus 2, Sn minus 3, like that. Then how we can get, because recurrence relations we have defined that a particular term, how it is related to its predecessors. That means, here how Sn is related to its predecessors, mean Sn minus 1, Sn minus 2 and so on. Now, how we can find Sn, because it should not contain 111. So, I can get Sn. So, we can get Sn that will form that it is the strings, the number of strings that begin with 0, number of strings that begin with 0, because it that do not contain 111. So, if it begins with 0, then it will not contain the 1 pattern. Then number of strings that begin with 10, then also it is violated. Number 3 is the number of strings that begin with 110, since that 111 it does not consider. So, I can write that expression, that Sn, I can write Sn equal to Sn minus 1 for the first case, then Sn minus 2 plus Sn minus 3. Then what will be my initial conditions? my initial conditions will be S1 equal to 2. Since only one bit S1, that it can be only 0 and 1. So, it is 2. Then what will be my S2? S2 will be 4, because these will be 0 0 0 1 1 0 1 1. Similarly, I can get S3 equal to 7. I can get S3 equal to 7, because here it will be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 and 1 1 0, but 1 1 1 will not be here. These will not be here, because so it has 7. So, the initial conditions, that S1 equal to 2, S2 equal to 4 and S3 equal to 7, I get the recurrence relation, that Sn equal to Sn minus 1 plus Sn minus 2 plus Sn minus 3. So, I can frame the recurrence relation when for Sn, which represents the n bit strings that do not contain 1 1 1. Now, we can see that different type of examples. Normally, it is very important that we call that a code word enumeration. So, we take another example. Of code word enumeration. See, a valid code word. So, a valid code word is a some n bit word having decimal digits. With even number of zeros. So, it is defined like even number of zeros. Now, we have to find the code word. So, let n be the number of valid code words. Then how we can get a relation or a recurrence relation. So, I can write that n, and here also I can get, see how we can get the recurrence relation of n, or how we can form the number of valid code words. So, it can be the first word, first letter or the first digit can be other than 0. So, there are 9 such digits can be there. So, 9 ways I can do that thing, we can do, and how many such we can get? So, this could be 9 n minus 1, because n minus 1 is again a valid code word. That means, we consider n minus 1 is the n minus 1 bit words having even number of zeros, and other things we can get, that the total number of code words So, if I can add a 0, total number of code words having n minus 1 bits. So, total number of code words with n minus 1 bits minus n minus 1, the valid code word. So, it will give me the total number of, invalid code words, the total number of invalid code words, with n minus 1 bit. Now, if we add one digit, the nth digit, say the nth digit as 0, then I will get a valid code word. So, I can tell that this 9n minus 1 and this total number, what will be that number? We can see that this number, total number will be the actually give me the n. Now, what is this number? This number will be, we know that since I have 10 digits, so this will be 10 to the power n minus 1 is the total number of code words minus valid code word is n minus 1. So, this is total number of invalid code words. This is invalid code words with n minus 1 bit, and nth bit we add is 0. So, my n becomes, n is 9 n minus 1 plus 10 to the power n minus 1 minus n minus 1, and this gives me 8 n minus 1 plus 10 to the power n minus 1. This is my recurrence relation. Then what is the initial condition? This is my recurrence relation. We can get that for A1, the initial condition is that A1 equal to 9 and A2 equal to some 81 plus 1. So, 10 to the power 0 is 1, that we can validate that it is equal to 82. So, we see a different type of examples and how we can frame or how we can design the recurrence relation for those problems. That means, given sequence, that how one term is related to the previous terms. So, next class we will see how we can solve the recurrence relations.